Per and polyfluoroalkyl substances, or PFAS, are a large class of highly persistent forever chemicals that are found in products we use every day. And a big problem is when one harmful PFAS is phased out after years of scientific research and advocacy, the likely replacement is another PFAS chemical with similar function, structure, and toxicity. The idea for this paper arose during a discussion of this regrettable substitution problem around PFAS at the 2018 Green Science Policy Institute Toxic Reduction Retreat. Participants from business, government, the nonprofit world, and academia decided to write a paper signing that all PFAS are persistent, likely to harm health, and should only be used when essential. We hope this paper, evaluating at a high level the potential for harm of the entire class of thousands of PFAS, which includes the large polymeric PFAS, will help retailers and manufacturers make better decisions around purchasing, and will assist government with the management of all PFAS as a chemical class.
Looking from the surface, PFAS are a diverse chemical class in terms of structures and properties. But when looking closer, PFAS share a key trait. They are highly persistent themselves, or they may transform to other highly persistent PFAS. This high persistence means that once PFAS are released, they accumulate in the environment. After decades of use, a huge reservoir of different PFAS has already been built up in the environment. The continuous use of existing PFAS and the introduction of similar new ones are contributing to growing levels of PFAS in the environment, and thus growing human health and environmental risks. Due to their high persistence, it is also very costly and technically challenging to reverse human exposure, if possible at all. Thus, we can fairly say when the risks are identified, it's already too late to do anything.
A myth that's been spread about PFAS is that human health effects from environmental exposures are unknown, and no human study has proven exposure to any PFAS causes any illness. This presumes that human studies are identical to experimental animal studies, where we control PFAS exposures and track health from start to finish. I've seen firsthand the havoc that PFAS exposure plays on animal physiology, increasing liver weights 2 and even more times normal, altering development, and minimizing their immune system's ability to make antibodies. This isn't limited to well-studied PFAS, but to PFAS now being identified in drinking water and food and detected in human blood. Studies of PFAS-exposed people show that they, especially children, also have a reduced ability to make antibodies to vaccines and get sick and hospitalized more often. This may lead to greater numbers of people with compromised immune systems, which is especially concerning during a global pandemic. Multiple observational studies of PFAS-exposed people are supported by these similar findings in PFAS-exposed animals. Therefore, the more appropriate scientific conclusion is that PFAS are human health hazards.
PFAS cause many health effects in addition to those in the liver and the immune system. PFAS affect our kidneys, our reproductive organs, our developing brain, our hormones, and our basic metabolism, increasing the risk of obesity and diabetes. And PFAS are associated with cancer, not only in laboratory animals, but in people. In fact, essentially all of the health effects seen in observational studies of people have been seen in laboratory animals. We all need to remember that when we study the potential effects of compounds, we have to consider not only the starting materials and the product, but what may result from their breakdown. The class of PFAS involves thousands of small molecules, but in addition, it includes polymers, which are what you get when you hook these small molecules together. Some of these will never break down and will be with us forever, just like styrofoam. All PFAS are persistent and accumulate in the environment, and all move throughout the world. As a result, there are PFAS in every continent and in every one of us.
The more we study PFAS in humans and animals and cells, the more we learn about the harm they can cause. With thousands of PFAS identified to date, we need a new approach to the costly and time-consuming method of studying one chemical at a time. Providing clean drinking water to contaminated communities is also expensive, but we will never clean up whole river systems that have been polluted by complex mixtures of PFAS. Eliminating non-essential uses of PFAS, for example in cosmetics or food packaging, will reduce the influx of harmful fluorinated chemicals to the environment, slowing the increasing levels in the environment and our bodies. Meanwhile, it will stimulate innovation towards safer alternatives and new cost-based strategies to clean up the environment. Progress is already underway in some countries. In the EU, Germany and the Nordic countries have proposed to take action to phase out all PFAS beginning in 2025. And the EU recently adopted a drinking water standard for all PFAS. The class-based approach is a feasible, scientifically sound, and efficient way of protecting health and the environment.